Welcome students. We are going to discuss about special congruences. The idea, the motivational point perhaps could be that if I give you a natural number n, how can you effectively determine whether it's prime or not? Similarly, if n is a non-prime, how can we effectively factorize it? Again, know that none of these goals will be met in this course. Uh, it is still a hard problem to find a way to effectively factorize a non-prime or a composite number. However, determining whether a number is prime or not is now a polynomial time algorithm. So let's start. So first theorem is basically Wilson's theorem. So Wilson's theorem tells us the following: if p is a prime, then p minus 1 factorial is congruent to 1 mod p. So let's see, what does it mean? Let's digress. So let's take p equals to 11. Now p minus 1 factorial in that case is going to be 1 times 2 times 3 times 4 times 5 times 6, 7, 8, 9, 10, and we are going modulo 11. So now notice the following. If you look at 2 and 6, so 2 6 are 12, which is 1 mod p, right? So inverse of 2 modulo 11 is 6. So when I multiply them, I will get 1 mod p. Similarly, 3 times 4 is also 12, which gives me 1 mod p. So these two, when you multiply, you get 1 mod p. Now, notice that 5 and 9, 5 nines are 45. 45 is congruent to 1 mod p, right? Because 45 is 1 plus 44. So you can pair these guys together as well. And then you notice that 7 8s are 56. So 56 is congruent to 1 mod p. So you can pair them too as well. So 57 times 7 and 8 are inverse of each other modulo 11. So these two can be paired as well. What is left out is 10, which is p minus 1, right? 11 minus 1, which is congruent to 1 mod p. Sorry, congruent to minus 1 mod. So certainly, you can see for p equals to 11, this theorem is true. We will prove it for all p now, all p prime. And notice the attack of the the way to attack the problem or this theorem would be the same as what we did with this problem. So let's start proving it. So first case is p equals to 2, right? So if p equals to 2, then we have p minus 1 factorial is 1 factorial, which is going to be minus 1 mod 2, right? So if p is 2, then you'll get 2 minus 1 factorial. So therefore, Wilson's theorem is true for p equals to 2. Now let p be a prime greater than 2, Then, as we saw here, 3 had an inverse modulo 11, which was 4, and it will be between 1 and 10. So same way, for any node, for any a between 1 and p minus 1, there exists what? There exists a bar, the inverse we are representing as a bar, with again a bar is also between 1 and p minus 1, such that a bar is congruent to 1 mod p. Yeah. Note that this theorem is true for even a composite number. Instead of p, you can have n. All you need is that a is relatively co-prime too. So now what we can do is the following. We can start pairing up. But before we pair up, we should say which ones pair with themselves. So the only positive integer which are inverse of themselves, which are the inverse, which are their own inverse, are a such that a is congruent to 1 mod p or a is congruent to minus 1 mod p. So in this case it will be r 1 and p minus 1. So therefore now we can start grouping them. So we can group starting from 2 all the way until p minus 2 into how many pairs? Into p minus 3 divided by 2 pairs of integers, such that product of each pair, so product of such that product of each pair is congruent to what? 1 mod p. And hence we have, if we take 2, 3 all the way to p minus 2, that is going to be congruent to 1 mod p. Right? Now multiply both sides by 1 and p. So you have, therefore, we have 1 times 2 into 3 blah 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 p minus 2 times p minus 1 is going to be congruent to so this part is 1, right? So this is going to be congruent to p minus 1, which is same as minus 1 mod p. So this is your p minus 1 factorial, right? Therefore p minus 1 factorial is congruent to minus 1 mod p. So this is the Wilson theorem. You'll see it's a very powerful theorem. It has applications everywhere, particularly for the remaining part of this lecture. You'll see how useful it is. So again, if p is a prime, then p minus 1 factorial is congruent to 1 mod p. So this is your Wilson's theorem. Yeah, of course, p has to be. Now let's ask the question, is converse true? What do we mean by converse? If this is true, then is p prime? And the answer is yes. If n greater than or equal to 2 is an integer such that n minus 1 factorial is congruent to minus 1 mod p, then n is a prime. Yeah. Note that this can be used as a first test for primality. primality to check whether a given positive integer is prime or not. Okay. Nevertheless, this is not an effective method, but still there is at least one method we know now. So let's prove this. So we'll prove by contrapositive, or we can use proof by contradiction. So suppose n is composite. So we'll prove by contradiction. So n be composite, and on top of that we have n minus 1 factorial is congruent to minus 1 mod n. Yeah. So if n is composite, let's see what happens. So if n is composite, since n is composite, this implies there exist A and B, both positive, right? With A strictly less than n and B strictly less than n greater than 1, such that, well, n equals to AB. Now note that since A is less than n, this implies A divides n minus 1 factorial. Yeah. Because then A is one of these 1 to n minus 1, right? Also note that since n minus 1 factorial is congruent to minus 1 mod n, this implies n divides n minus 1 factorial plus 1. So this would mean what? So we have A divides n, and n divides n minus 1 factorial plus 1 implies by transitivity. So transitivity of division, we'll see that A divides n minus 1 factorial plus 1. But now notice that from this part we have A divides n minus 1 factorial. From this we get A divides n minus 1 factorial plus 1. So A divides the linear combination of them, right? But we need special kind of linear combination. So that means A divides linear combination of this. So n minus 1 factorial plus 1 minus n minus 1 factorial. Yeah, so n divides this guy. Yeah, let me just make the bracket clear. So n divides this, but this implies A divides what is left out? 1, which is a contradiction, since n is what? Since A is bigger than 1, right? So therefore our assumption must be wrong. Therefore our assumption is wrong, which is a contradiction. So our assumption is wrong, namely n must be prime, right? Must be prime. So that proves the converse of Wilson's theorem. The next theorem is called Fermat's little theorem, not the last theorem. Okay, so Fermat's little theorem. So if P is a prime and if A is an integer such that P does not divide A, then A to the power P minus 1 is congruent to 1 mod P. So let's prove this. So start with the following. So consider p minus 1 integers a, 2a, 3a, all the way until p minus 1a. Yeah. Now, none of these are divisible by p. None of these are divisible by p. Yeah. Because if p divides sum of one of these, say, let's say I times a, where I is between 1 and p minus 1, this would imply p divides I, since p does not divide a, right? If this result is true for prime, right? That if p divides ab, then either p divides a or p divides b, right? Since p does not divide, but this is not possible. Not possible, since your I is between 1 and p minus 1. So therefore, none of these are divisible by p. Now note that none of them are congruent modulo p as well. So this is claim 1. Claim 2, none of these means what? None of a, 2a, dot, 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 p minus 1a are congruent mod p, are congruent modulo p. Why is that? Suppose ai is e congruent to aj mod p with, say, I less than j without loss of generality. This would mean p divides what? P divides ai minus aj. That is a definition. This means p divides a times I minus j. This implies p divides I minus j, because p does not, since p does not divides, again, p does not divides a, and p is a prime, right? So this is not possible, since I and j are both positive integers less than equal to p minus 1. Yeah. So note that. Why is that not true? So let's see. So let me just digress on this little bit more. So I have p divides I minus j. This implies I equals to j. So we get I equals to what? J plus some p, j plus some kp. Yeah. Or because j is bigger, I will write it this way. J equals to what? I plus kp. Now that is not possible, right? Because both of them are within what? So k has to be positive for this to work. For this to work, k has to be positive, but that would mean that j definitely has to be bigger than p. Right? So none of these are congruent modulo p. So that is also so. So with that, if you go modulo p, so Therefore, by a theorem, what should happen is these numbers a to a dot 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 p minus 1a. So this means that if you take a dot 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 p minus 1a by a theorem, these are what? These must be 1, 2 dot 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 p minus 1 modulo p in some order, of course, in some order. Yeah. So therefore, what do we get? On one hand, when I take a to a dot dot p minus 1a, on one hand, so this mod p is going to be congruent to 1, 2, 3, p minus 1. Yeah, because this is equal to, so these a to a blah 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 are must be 1 to p minus 1 and all of them modulo p. So now let's see on this side, on the left hand side, you get a to the power p minus 1 times p minus 1 factorial. On the other hand, you get p minus 1 factorial mod p. But note that GCD of p minus 1 factorial, so since GCD of p minus 1 factorial and p is 1, this implies we can divide both sides by p minus 1 factorial. So we get a to the power p minus 1 is congruent to 1 mod p. So this is your theorem proved. Okay. So again, the idea in this theorem is that if you take a to a blah 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 p minus 1 a and you multiply them out, they are essentially 1, 2, 3, 4, 5, 6, 7 dot 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 p minus 1 in different order, right? Modulo p, of course. And then you multiply on both sides and you see you can cancel p minus 1 factor. So we get the following, right? Now, let's look at the next result. Namely, if p is prime, then a to the power p minus 1 is congruent to 1 mod, sorry, it's congruent to a mod p. Yeah, where a is what? A is a positive integer. We don't even need the co-prime part. Now, how do we go about it? There are two cases now. Here we are not assuming that a is co-prime. So case one, if a and p are co-prime, that means p does not divide a. This implies a to the power p minus 1 is congruent to 1 mod p. Yeah. Fermat's little theorem. And then multiply both sides by a. This does their job. So you get a to the power p is congruent to a mod p. Case 2, I should have rather written it, even though they're the same thing, p does not divide a, and case 2 is p divides a. If p divides a, this means what? A is congruent to 0 mod p, and raising it to power p as well. So a to the power p is also congruent to 0 mod p, 0 to the power p, which is same as saying a to the power p is congruent to 0 mod p. Now, these two are equal. So therefore, we get a to the power p is congruent to a. Now an example of this. So why is this interesting or useful? Let's say basically you have 3 to the power 201 mod 11. You want to find out using Fermat's little theorem. So this would mean, first of all, we know that. So how do we prove that? Find. So for that, notice the following, that A, so since 3 does not, so since 11 does not divide 3, 11 is a prime, and 11 is prime. This gives us 3 to the power 11 minus 1 is congruent to 1 mod 11. That means 3 to the power 10 is congruent to 1 mod 11. Now, what do we do with this information? So this means 3 to the power, now divide, so apply Euclidean algorithm. So 201 is equal to 10 times 20 plus 1. So what do we get? So this implies 3 to the power 201 is congruent to 3 to the power 10 times 20 plus 1, which is congruent to 3 to the power 10, the whole power 20 times 3, which is going to be, now 3 to the power 10 is 1 mod 11. So therefore, it's going to be 1 to the power 20 times 3, which is congruent to 3 mod 11. So you're done. Now, so if P is a prime and A is the integer such that P does not divide 0, then A to the power P minus 2 is inverse mod P. Now appreciate this result. Why do we need to appreciate this result? I mean, if you go back here, we paired the integers with their inverses, right here. We paired them. But the pairing was in some sense ad hoc, really. You checked out all of them, right? So essentially you are checking all of the elements and trying to see which one is inverse of what. However, here you get the inverse right away. So inverse of A is A to the power P minus 1. Sorry, inverse of A is A to the power P minus 2. Yeah, how do we see that? So if P does not divide A, then we get A times A to the power P minus 2 is equal to or congruent to A to the power P minus 1. And that is congruent to 1 mod P by Fermat's little theorem. I'm tempted to write for FLT, but FLT stands for Fermat's last theorem. So what we gotten here is that A times A to the power P minus 2 is congruent to 1 mod P. So hence we get A to the power P minus 2 is inverse of A mod P. Of course, that is the case when P divides A. Yeah. If P does not divide A. If P divides A, there is no inverse. We already know that. So there's no point of thinking about that at all. All right. Okay, so for that, what would be the example? So if you're going modulo, so we already found out, say, let's say, go back here again. We saw that 2 and 3 are inverse of each other modulo. Sorry, 2 and what? So we found out 2 and 6 were inverse of each other modulo 11, right? Because 2 times 6 is 12 and 12 is congruent to 1 mod 11. So let's see how Fermat's theorem helps us out. So example. So notice that 2, we are looking at inverse of 2. So inverse of 2. So example, inverse of 2 modulo 11 is 2 to the power 11 minus 2, p minus 2, right? Which is going to be 2 to the power 9 mod 11. Yeah. And if you look at 2 to the power 9 mod 11, so this is going to be 2 to the power, you can now break it into parts. So 2 to the power 5 times 2 to the power 5, sorry, 2 to the power 5 times 2 to the power 4 mod 11. Now 2 to the power 5 is 32. So 32 mod 11 is minus 1, right? Because 33, so minus 1. 2 to the power 4 is 16. So 16, which is going to be mod 11 is going to be 5. And then that can be written as minus 1 times, so minus 5. Minus 5 is equivalent to 6 mod 11, because we have to produce an integer between what? Between 1 and p minus 1. So therefore, inverse of 2 is 6. Now, the above theorem helps us to solve certain linear congruences very quickly. So let's see the following. So let a and b be the positive integers, and p be a prime, and p does not divide a. Then you're looking for the solution to ax congruent to b mod p. Now so p does not divide a. This implies a has inverse modulo p, or rather a has an inverse as a to the power p minus 2 modulo p. So multiply both sides by this inverse. So we get what? If you multiply both sides by this inverse, you get a to the power a times a to the power p minus, my bad, a to the power p minus 2 times ax is congruent to a to the power p minus 2 times b mod p. So now this would give me a to the power p minus 1 times x, which is same as a to the power p minus 1. A to the power p minus 1 is 1 mod p, right? Because p does not divide a. So this will be x, which is congruent to a to the power p minus 2 times p mod p. So you have already found out x, namely you found out the solution to this linear congruence. Okay, so modulo p is easy to deal with. So now the question is, if p is prime, so we already have seen if p is prime, then a to the power p minus 1 is congruent to 1 mod p. So is converse of this statement true? Is converse true? That is, if a to the power p minus 1 is congruent to 1 mod p, is p a prime? If that was the case, then it would have given a new test for primality, and the answer, unfortunately, is no. So there are something called as pseudo primes which satisfy. So there are some numbers which satisfy this without being a prime. So those are called pseudo primes. So no, yeah, we'll discuss later. So unfortunately, this is not true. Otherwise, it would have given us a nice primality test. So let's see an extension of Fermat's little theorem. What is Fermat's little theorem? If p is a prime and a is an integer with p does not divide a, then p to the power 1 minus p to the power a to the power p minus 1 is congruent to 1 mod p. Now, what could be the reasonable generalization of this? Yeah. So we can let go of the fact that p is prime, but then is it result true? Or is there some power which will lead a to the power that number is congruent to 1 mod p? And the answer is yes. That is what is the Euler's theorem. So let's see. So first, let's set up the premise for the Euler's theorem. So let n be a positive integer. Then define Euler phi function, so phi of n, to be number of positive integers not exceeding n that are relatively prime to n. For example, let's take phi of, say, phi of 6. Phi of 6 is going to be, what are the numbers not exceeding 6 and relatively prime with 6? So phi of 6 is number of the elements which are positive integers. So of course, what are the numbers which are relatively co-prime to 6 and less than 6? So 1 is there, 2 no, 3 no, 4 also no, 5 yes, and 6 of course is not co-prime with 6. So phi of 6 is going to be size of this set, which is 2. Yeah. Note that for phi of a prime p prime is going to be size of 1 dot 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 until p minus 1, right? Because everything which is less than p is relatively prime with p. So phi of p is always going to be p minus 1. So question is, what about m is composite? So question, if m is composite, what is phi of m? I mean, like, that's a generic question, or let's say the better way to say that is ask a question is what or how do we calculate, how to calculate phi of m? I mean, of course, effectively. Again, I'm throwing this word effectively, but we'll see how to do that. So let's have another definition. So a reduced residue system modulo n is set of phi n integers such that each element of the set is relatively prime to n, and no two different elements of this set are congruent modulo n. So this is what reduced residue system modulo n is. Say, for example, in this case, what is a residue system? So reduced residue system modulo say 6 is just 1 and 5, right? Why? Because first of all, it has to be relatively prime to 6. So only possibilities 1 and 5. And you can see that no integers which are less than 6 are gonna be congruent modulo 6, right? So all you have to do is compute this phi n and list all the relatively prime to 6. Okay. So let me give another example, say mod 9, the reduced residue system modulo 9. So let's just say reduced residue system modulo 9 is going to be what? So one example is 1. So then 2 is okay because it's relatively prime with 9. Then next one, 3 not okay, 4 is okay. Then 5 is also okay. 6 is not okay because not relatively prime to 9. 7, yes. 8 also yes. So there's one example there. Well, another example would be multiply this by, say, 2. So 2, 8, 10, 14. So these are also phi n integers, which are each element is relatively prime with n, which is relatively prime with 6, right? Each of them are relatively prime with 6 because none of them have factor of 3 and none of them are congruent modulo n. Yeah. For that, remember you had a theorem which said that any affine transformation, so any affine transformation will also, or as long as the A is not A and N are coprime, you get a residue system as well. So let's prove this theorem. So if R1, R2, R3, dot, 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 R phi n is reduced system modulo n, and if n is a positive integer with A and N are coprime, then AR1, AR2, AR phi of n is also reduced system modulo n. All right. So let's try to prove this. So proof. So we have to show, so we are given this. Suppose ARJ and N. So we want to show that, what do we want to show? That these are also reduced residue system modulo n. We want to show that, this is also one. To show. So let's assume, so suppose not, if not, what do we have is ARJ and is greater than 1. So we have a theorem saying that if we take any number which is bigger than 1, it has a prime divisor. Yeah, this implies there exists a prime divisor of ARJ, and this means, let's call that prime divisor P. This means what? This means P divides A, RJ, and P divides N. But the first one implies P divides A or P divides RJ. Yeah. So what we have is, out of this, we get either P divides A and P divides RJ. Sorry, P divides A and P divides N, or P divides A, sorry, my bad, P divides RJ and P divides N. Now, first one is not possible. So one is not possible since these are coprime, right? Now, so 1 is not possible. So what about 2? 2 is not possible since what? Since RJ is a reduced residue system. So it's a residue is a reduced residue system modulo n. Yeah. So therefore, what do we get? Therefore, we get ARJ and N are relatively prime. Now we want to, so that's one. So now second thing we want to show is that none of these ARJs are congruent modulo n. So to prove that, so we want to prove no two of ARJs are congruent modulo n. Yeah. Why? For if ARJ is congruent to ARI mod n, right, with I and I not equal to j, and they are between 1 and phi of n, this would imply A times R j minus Ri is congruent to 0 mod n. Now note that A and GCD of, now this is implies Rj minus Ri is congruent to 0 mod m. Why? Because A and N are co-prime, so you can do the cancellation theorem here. It looks like, okay. So this implies Rj is congruent to Ri mod m. Now this is not possible. This is a contradiction to fact, since Ri and Rj are from the original set of reduced residue system modulo n. So what have we proved here? So we have proved that, first of all, if you take these are reduced residue system modulo n, you multiply with A, where A and N are co-prime, then A times R1, A times dot dot dot, A times R phi of n is also reduced residue system modulo n. Right, and how did we achieve this? We proved that if you take this new set of integers here, AR1, AR2, ARPN, we have shown one, that they are relatively co-prime with n, and also there are phi n of them which are not congruent modulo n. So they are not congruent to each other modulo n. So we have produced a new set and we are done. Now, a straightforward consequence of the last theorem is Euler's theorem, which is the generalization of Fermat's theorem. So generalization Fermat's theorem. So again, instead of prime, let A be a composite integer and, sorry, M be a composite integer and a is an integer such that a and m is GCD of them is 1, then a to the power phi of m is congruent to 1 mod m. This is Euler's theorem. Right? So if I look back here, you can see that if m is p and a and m being co-prime translates to what? Because a and p is 1, but p is a prime, this is same as p does not divide j, then phi of n, as we saw already, a of p is going to be a to the power p minus 1, which is congruent to 1 mod p. So Fermat's theorem is a special case of Euler's theorem. Okay, so let's prove this. So proof: let R1, R2, R phi of n denote reduced residue system where Ri's do not exceed n, right? We created one for any n. Now, since a and m is 1, we'll see from previous theorem, even a R1, a R2, a R phi of n is also a reduced residue system modulo m. Hence, if you go modulo n, the reduced residues, therefore, the least residue, that means if you divide if you go AR1 mod n, and you look at the least residue, that means the remainder, the least residue of AR1 to AR1, so AR phi of n is equal to, must be these integers, right? So must be equal to, or must be integers R1, R2, R phi of n in some order. So if you multiply on both sides, so we get therefore AR1, AR2, dot, 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 AR phi of n, that is going to be R1, R phi of n mod m. So this implies A, how many A's are there? Phi of n of them. R1, R n, phi of n is congruent to R1, R phi of n mod. Now note that Ri m is 1, right? Because these are relatively prime to m. This implies for all I, right? For all I from 1 to phi of n, this implies R1, R phi of n is relatively prime with n. Therefore, you can use the cancellation property. So therefore, we get what? A to the power phi n is congruent to 1 mod n. Now, this is very powerful in some sense. Why is it powerful? Let's see example. Say you want to see what is last digit of 3 to the power, say 8 mod. So what is the last digit of 3 to the power 8? So you're asking, that is, what is 3 to the 8 mod 10, right? So we know that 3 to the power phi of 10. So solution to that is phi to the power 3 to the power phi of 10 is going to be congruent to 1 mod 10. Now we need to compute phi of 10. So phi of 10 is going to be, now we need to come up with a nice formula for it, which we'll do soon. However, for now, let's just do by enumeration. So 1 is there, then what else? 2, no, 3 is there, 4, no, 5 is not there, 6, no, 7, yes, 8, no, 9. So phi of 10 is this, so we get 3 to the power 4 is congruent to, so therefore phi of 10 is basically size of this set. This means phi of 3 to the power 4, which is 4. So 3 to the power 4 is congruent to 1 mod 10. Raising both sides by 2, I get 3 to the power 8 is congruent to 1 mod 10. So therefore the last digit is last digit is 1, right? So now we need an effective algorithm to compute phi of n, right? Okay, so that's one thing. Similarly, so note that this problem could have been done by Chinese remainder theorem too. Yeah, so doing same thing again, it's a digression away from the usual context of the thing, but let's compute using Chinese remainder theorem. So let me just hint on that. You compute 3 to the power 8 congruent to 2, sorry, congruent to what mod 2, and then you compute 3 to the power 8 congruent to y mod 5, and then combine these two, combine x and y using Chinese remainder there. So that's all for now. Thank you very much for your attention.